Here's the continuation of topology investigations. We got to the point where we were gluing a rectangle in various ways and determined that probably the funkiest way to do it is to flip both. Glue A to A with a flip, B to B with a flip. And I claim there's another way to understand that, another way to see why that would appear. Look at the eraser. And it comes from classical geometry, in a way. Some very, very basic facts about geometry is that 2 points, this is plane geometry, determine a line, and that's 2 distinct points. So you just repeat the same point twice, that's not going to work. And 2 distinct lines determine, by intersection, a point. Right? Well, think about this one for a second. Is that really true? Is it always true? Pretty quickly you can figure out that's not always true. There's a special case when you have 2 parallel lines. They don't intersect. And it seems like a minor point, but it's a very beautiful thing that we can actually fix this and make this much more parallel. That 2 points determine a line, and in fact we can say, how do they determine it? There is a unique line, say this is P and Q, there's a unique line such that P and Q sit inside of L, are elements of the set L, because L is a set of points. And except for the parallel case, given 2 lines, let's say L and M, there's a unique point, P, which is in the sets L and M. And so it's just very tempting to see these as dual. So here's the 2 small things to determine a bigger thing. Here's the 2 big things to determine one small thing. And it's just an annoying special case. Another way to say it is something we see a lot in like trig problems, geometry problems. Like I was doing this in another class. You have a lighthouse on a little rock off a straight coast. And if you look at where the beam hits, as the angle increases smoothly from, let's say, 90 degrees, or let's say, 90 degrees here, and as this angle decreases, well, eventually they become parallel, and the point of intersection moves off to infinity. And it's this annoying thing that there's this special case where we say, oh, we can't define the intersection. Blows up, D and E, undefined, asymptote. And it'd be a wonderful thing if we could actually not have to do that. Well, projective geometry, the projective plane, is a way to do that. And there's many ways to understand projective geometry, and you need all of them if you're actually going to do it for a living. A lot of people do. But one way to understand it is we're going to just add those points in. We're going to say if 2 lines are parallel, we're going to say they intersect at infinity. And you could think of it as kind of this natural limit process, that if they weren't parallel, they would intersect farther and farther and farther and farther out, and we're going to say there is some point that they intersect at. So we're going to add a special point at infinity where those lines are going to intersect. Now, how many points at infinity should we add? Well, these guys are parallel lines in a certain direction, and they're going to intersect in a point at infinity in that direction. And you might think, well, maybe I can just add one point at infinity, and everything's going to intersect at that point at infinity. Well, that messes things up. You actually have to pay attention to the direction that things are going in. It turns out that if you have another pair of parallel lines, then you add another point, some other point at infinity, for them to intersect at. And so on for every pair of parallel lines. Well, essentially, for every direction, you're adding a point at infinity for every direction. So these 2 guys intersect at this point. And so do these things. These two lines, all those pairs intersect at the point at infinity that's determined by that direction. And so here's one way to get to infinity, here's one way to get to infinity. Now notice, if I want this to be true, that they intersect at exactly one point, I should not add a point out here in this direction in infinity and a different point over here. These should be the same point, because that's that one and only point of intersection of those lines. It seems pretty weird that you can just artificially add these points at infinity. And it's not really that weird. Why not? You can just say a lot of things are true. But what is interesting is that it works, it makes sense, it's a kind of geometry. Many familiar facts about lines and points are still true, and it means that this is always true. And it turns out that a good way to think about it is that what you're adding is a whole line's worth of points at infinity. So there's actually a whole line at infinity. Now, when you picture lines, it's really hard to picture a line at infinity because there's nowhere to put it in your head. But it turns out that formally, in terms of these kinds of properties, it behaves exactly like a line does in this geometry. So, might seem like a curiosity that you could be able to do that. But it turns out that when people do modern geometry, many, many different kinds of modern geometry, very, very often they're going to make this kind of assumption. Because once you get used to it, it doesn't complicate your life, it simplifies your life dramatically by never having to say D and E, basically, and never having to say, oh, there's no solution. So, what does that have to do with what Jerry Lear was talking about? Well, if you take to a topologist, now let's think about how a topologist would think about this. You've got the plane R2. That goes off infinitely far in all directions. Okay? But to a topologist, there's no such thing as distance. To a topologist, going off infinitely far just means you'll never hit the edge. And so, to a topologist, it turns out that working with R2 is just as good as working with a disk, as long as you're very careful not to include the boundary of the disk. If I start at the center, and I just agree that to sort of simulate going off to infinity in the ordinary real line or the ordinary plane, I just agree to go off, and I just get slower and slower and slower and slower and slower and slower. And if I go slower enough, then I'm just never going to reach the edge. And so it turns out that this is equivalent to what we call the open disk. Open meaning doesn't include its boundary, roughly. Has a fuzzy edge. Okay. Now, what was the geometer wanting to add on to R2? It was adding a point at infinity for every direction. Basically, every line, every way a line can be put in here, every attitude a line can have, there's adding one point at infinity. So one way to do that is you stick a line in here, and you say, I've got to add a point. Oh, there's a convenient place to put that point, because I purposely didn't include an edge to make it feel like it had this fuzzy edge that you could never get to. But now I'm actually going to put the edge in. That's going to be a point at infinity. And for this line here, I'm going to add a point at infinity. For this line here, I'm going to add a point at infinity. Oh, doesn't that just recreate the disk? Am I not just going to get a circle's worth of points at infinity? Well, remember, this point at infinity is supposed to be exactly the same as this guy. Because like the two parallel lines here are supposed to intersect only once. And so there's supposed to be one point at infinity. So this point A is really the same added point I would add here. And let's say this guy here, this is added point B, it's supposed to be the same as this guy. So what I'm getting, topologists would say, I'm going to take a disk and I am going to include the boundary. What's called the closed disk. And I'm going to identify any point with its antipodal point, its opposite point across the circle, the other end of the diameter. And let's see, to a topologist, that's the same thing as if you took that disk, sort of squashed it, squared off the corners, and let's see what kind of identification that makes on the corners. It means that a point here gets to a point here, a point here goes to a point here, a point here goes to a point here, a point here goes to a point here. Those diameters just turn into going sort of through diagonals on the square. And so that means that this edge and this edge are identified, but remember, with a twist. And similarly, every point here, just like this point goes to this point gets glued to this guy. This to this, this to this. And so what we get back to is this idea of taking a rectangle and putting it together with a twist. Turns out that to a topologist, that's exactly the same idea as taking all of infinite space, adding points at infinity to make linear geometry, straight lines and points, work nicely. And so, and that's important. The geometer, if they're asking really interesting, subtle questions about projective geometry, about that weird system of geometry, they're gonna need to know what kind of topological shape it is. Does it have edges? Does it have holes? What happens if you go around and things flip, and the thing about the R flipping that I showed before. So it turns out that that's why this example, let me do it one more time, whoops. That last thing on our list is called the projective plane, sometimes called the real projective plane, because you can do it all with complex numbers and it gets very interesting, but I'm not going to talk about that. Okay, let me just do one more of these gluings, because it's just cool and simple. You might have wondered, do I have to glue across opposite faces? What if I glue like this? Oh no, let's see, this way. That way, yeah. What if I glue it like this? How about A to A, B to B? Think about that for a second. Maybe pause the video if you don't want the answer right away. Well, what happens if, think about this as fabric, and this as this whole thing as a zipper that happens to have a little corner in it, and this as it's the other half of that zipper. If you zip it up, you're sewing this up, zipping it up, and there's a pouch that's kind of left, you get the sphere, you get the two-dimensional sphere. Which is nice, because that's the simplest two-dimensional closed shape with no edges that there is. It's nice you can get it from this kind of technique. Okay. So, let me just say a couple more examples of this idea, because it's so cool. Here's an example of this thing. I don't think I'm going to show you the details of why this happens. Let's just leave this as a super cool thing. I'm going to use this pattern. I'm going to do 4 pairs here. And this is a bit like what we were doing with the torus. If you actually just look at this part, and if I had actually closed it up here and not made an octagon and made a square, you can look at this and compare with what we did with the torus. And you can actually convince yourself that that's actually exactly what we did to create the torus. Similarly, this half here, if this guy were actually closed up, it would actually make a torus. That's the start of the proof, that if you do all 4 pairwise gluings, what you get is a double torus. Something with 2 holes in it and not just 1. And you can get that by gluing 2 tori together, and it turns out that that's how you kind of understand why this might give you that. And you can do the same for higher dimension, for higher polygons, a bigger number of sides, and get shapes with more holes. That might feel a little bit like one of the things that we saw on Friday, which is kind of the motivation where this all came from. That was a hexagon, which was actually thought of as the surface of a sphere, the surface of a cube. I'm thinking like a topologist, as you can tell. Let's say like that. Suddenly that hexagon is a cube. Think about it, that's coming towards you. Isn't that cool? That it was a hexagon, and now it's a cube. And what Jaron Lanier said was, if you take the 3 faces of a cube that are in front, and then just glue this to this, glue this to this, and glue this to this. So then you get a projective plane. And that is indeed what you get. And I think I'm going to do a computer video to do more about that.